So we are going to be determining the work required to empty out this full tank of water. What's kind of funny about these problems is that it's a bit simplistic because there's really no explanation of how the water is being pumped out, but that's okay. We're going to solve this like we're just a regular old Calc 2 student. So first, let me explain the steps that I'm going to take to solve the problem. So first, I want you to think of our Riemann integral and how we usually think about finding the area under a curve. So say I have this interval here, and here's my curve, and I want to find the area under the curve. The way that we think about this is that we cut it up into really tiny slices, and then I add up the area of all the slices to get the total area. So I'm going to do something very similar, but with volume. So my first step is going to, well, I'm going to take a sample slice from my picture. And my first step is going to be to find the volume per slice. Now, this is going to depend on the shape of the tank, so it would change from problem to problem. Then the next thing that I'm going to do is use this volume to find the force per slice. Now this, we think of our force as mass times acceleration. And so this is going to be the weight density multiplied by that volume that we found in the first step, and then multiplied by gravity, okay? And now the weight density and gravity was provided for you in the statement of the problem. And we're also going to need the distance per slice, which is basically going to be how far my slice travels to get to the top. Now we're going to use those two pieces to get the work per slice. Because remember, work is your force times your distance. And then we'll be able to take the sum of all these slices and get the total work. So first, let's get ourselves set up over here with the picture. Now, the way that you orient your picture is going to change the way you solve it a little bit. So I always like to make my orientation that the top of my tank is 0. And as I extend downward or dive into the tank, X is increasing in that direction. So that's how I'm going to orient myself. And so let me take a sample slice. It shouldn't matter where you take it. I just want to be able to write on it. So I'm going to take it a little further up so that it's a little bigger. So there's my sample slice. And, you know, it would go towards the back here like this. There we go. And my first step that I wanted to do was to find my volume per slice. And so I need to think about what kind of shape I get when I cut out a slice. So notice that how wide my slice is, it gets wider towards the top of the triangle and skinnier towards the bottom. But if I say that the thickness of my slice is delta x, and we're going to let delta x be really, 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 really small, then I can kind of pretend that this triangle isn't going to mess with anything, and I'm actually just going to have a rectangular prism. And so my slice is a rectangular prism, and I will find that the volume is length times width times height. Okay? And let's see what happens here. So the length, I'm going to say, is this kind of long side. No matter where I take my slice, that should be 6 meters. Now this portion here is going to be my width, so this small little piece here. And we're not sure what that is because it's going to change depending on where I took my slice. So that'll just be W. And then I already said that the thickness is delta x, so the height here is delta x. Now, because I oriented it this way, oops, I accidentally left this out. I'm going to say that from the top of my tank to my slice is going to be xi. Okay, so wherever I take my slice, the distance from the top all the way to my slice is going to be positive xi. Okay? And so that tells me that I'm going to have to solve for W And it should be a function of xi because the width is going to depend on where I took my slice. I'd say that this is the trickiest part of these problems. Following this little chain of arrows is pretty simple, but you're always going to have to be looking for this one of your variables here in terms of xi, and that can be a little bit tricky. So let's work on that. So I'm going to find w. And once again, I expect it to be a function of xi. So what I'm going to notice here is that this bigger triangle, which is the face of my tank, I have a lot of information about it. I know all of its dimensions. And so I'm just going to use similar triangles to figure out what W is. So first, let's take the face of the tank. I know that it's 4 meters across the top, and I know that it is 4 meters tall. So from top to bottom, it's 4 meters. And now let's look at our smaller triangle with the slice, right? So I know that it's W at the top. That's what I'm trying to solve for. And I'm thinking that I can figure out what my height is. So what is my height going to be? We know that it's going to be somehow related to xi. So if the whole thing is 4 meters tall, and this distance is xi, then my height of my smaller triangle, which is right here, so from here to here, must be the whole 4 meters, but then subtract that little red line. So 4 minus xi. And now since these are similar triangles, I can just take I can take ratios and solve for w. I'm going to take 4 over 4 is equal to w over 4 minus xi. Now it's just coincidental that both of the dimensions here were 4, so just be careful. The w is in the numerator, so this width should also be in the numerator. And then since my height is in the denominator, this height should also be in the denominator, so just make sure that they're matching up. And so when I solve for w, I get that w is equal to 4 minus xi. And now I can take that and plug it into my volume per slice. So now I know that my V slice is equal to 6, 4 minus xi delta x. And so I've completed my first step. Now my second step was to find my force per slice and my distance per slice. So I'm going to find my force. I'll write this down again. It's going to be our weight density multiplied by my volume per slice multiplied by gravity. Now my weight density is 1,000. My volume per slice was 6, 4 minus xi delta x. And then for gravity, it said to use 9.8. Maybe I should add something in here. I tend to not carry my units all the way through the problem, which is probably bad practice. You may want to be writing down all your units, but I'm just a little bit lazy. It's probably the pure mathematician in me that doesn't want to write down my units. And so at the end, I just kind of will put that it's joules because I know I'm in metric. So you may want to try keeping up with the units. And so let me simplify this a little bit. Let's multiply the 1,000, the 6, and the 9.8, just to make things a little simpler. So when I multiply all of those, I should get 58,800. 4 minus xi. I'll keep my delta x at the end. Okay, so I'm almost done with my second step. I wanted to find the force per slice and then also the distance per slice. Now, what I mean by this is how far does the slice have to travel to get emptied out of the tank? And so I'm going to come back up to the picture and look at how far it has to travel. So with my example slice, it has to travel xi to get to the top. But then I do have this 2-meter spout, so it has to go 2 meters more, so xi plus 2. Alrighty. And now we're ready to move on to the last step. Well, my last step that I included at the top there, which is just the work per slice, which is going to be my force times my distance. I could write. And so I'm just going to put this and this multiplied together. I am going to rearrange the terms a little bit. I'll keep my constant at the front and delta x at the end. So I have 58,800, and I have 4 minus xi 2, or sorry, xi plus 2. And then I'll keep my delta x at the end. And now this is the function that we're going to be integrating. So let's just simplify it now so that we don't have to do it later. So I'm going to go ahead and FOIL this set of parentheses here. So I'll keep my constant. Now when I FOIL this, I'll get a 4xi and a negative 2xi. So that'll leave me with a 2xi. The xi's together give me a negative xi squared, and the constants, when I multiply them, I just get 8. I have my delta x. And now I know the work necessary just for a single slice, but I need my total work. And I mentioned how we go about finding the area under a curve, so I'm going to do something similar here. So I'm going to say to get my total work, I need to take the sum of all of the work necessary for my slices. I'm going to rearrange these just for my own, just so to make myself happy, but you could leave it in the order we already had it in. Another thing that I should mention is it probably would have been more appropriate to call that xi star, but it just gets a little bit crowded, so I just left it as xi. Okay, so I want to add up all my slices. And first we're going to say, let's just say we have n slices. But then similarly to how we find the area under a curve, I'm going to say, but I want my slices to be really, 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 really tiny. In fact, I want them to be as tiny as possible so that my estimation is perfect. And so I take the limit as n goes to infinity, which is just going to keep shrinking down the size of my slice. And now this is just the definition of our Riemann integral. And so I'm going to integrate this function here. And I am going to integrate from the bottom of my tank to the top. Now notice that I just did 0 to 4, which was how tall my tank was. But the spout also has 2 meters, but I included that here, right? So it's already taken care of. So I'm going to integrate from 0 to 4. And now it should be pretty simple from this point. We're just going to integrate. So I have 58,800. And now we're just going to use our power rule. So I have a negative x cubed over 3 plus 2x squared over 2 plus 8x from 0 to 4. Now this is going to go ahead and simplify. And let's just finish this up. So when I plug in 4, I get negative 4 cubed is 64 over 3 plus 4 squared is 16, 4 times 8 is 32. And I am leaving off the 0 only because when I plug in 0, I'll get 0 plus 0, or negative 0 plus 0 plus 0. And so I do need to evaluate at the lower limit, but it just doesn't add anything on. So I'm just going to kind of ignore it. Okay, and so this you'll probably have to put into your calculator, and we get 1,568,000. And like I said, I was super lazy with the units, and I usually am, but you should probably keep up with them more than I do. I'm a bad influence. And so I am calculating work in metric, so I know that this should be joules. And there we go.